So I actually cannot hear you. Okay, probably I'm speaking. So let's start. So once we have created a programming language, there are many questions that are interesting to ask. Is my programming language type safe? Is it strongly normalizing? Is it free of data races? And so on. And so part of language validation, an important part of SLE, is to answer these questions once we have created a language. Now, I said language definition just to set the scope of the paper, because language definitions can be, I can use the notational semantics and so on. So we are speaking about operational semantics. So here we have an example. A functional language with booleans, lists, functions, and pairs. So list with the head operator and pairs with the first and second. So it's a grammar and inference rules for a type system and reduction semantics. Now, with a language like that, we can prove properties. For example, type safety. For example, progress. And just to see an example with progress, because we observe that language proofs. Some language proofs follow a schema that applies not just one language, but to a class of languages. So here we can see the example with the progress theorem. So if the expression is well typed, it's either a value, an error, or takes a step. So it's by induction, and after induction we have all the cases. And at line 4, for example, we have the case for the operator head. Now, by inductive hypothesis, we derive that the argument of head is also either a value, an error, or takes a step. Okay, and the first case is whether it's a value, and the way we proceed with the proof is that we apply the canonical form for lists. This will give us two cases for the two canonical forms for lists, which we are going to appeal to the existence of a reduction rules, a reduction rule for them. Now, if we continue the proof, for example, at line 11, and we hit the operator first, we do the same. We derive that the argument of first progresses as well, so it's a value and so on. This time we apply the canonical form for pair. We have only one canonical form, so we appeal once to the existence of a reduction rule. So here, whether we have head or first, in general, when we have, we can write this proof that if it is an elimination form of some type C, what we have to do is to apply the canonical form lemma of the type C, and for all values of the type C, we appeal to the existence of a rule. So now the question is, can we create a DSL to express these proof schemas in generalized so that they apply to classes of languages rather than one language? And in the paper we have developed Langenproof, a DSL for expressing this type of proofs. We offer an implementation and we offer an evaluation. We have applied the Langenproof to type safety proofs of a certain type of a certain class of functional languages, but we didn't manage to capture the whole type safety. We will speak about that, and we will also speak about the class of languages that we target. Now, before we go, I want to mention that our primary goal is not automated proving, so generating proofs automatically. So why I say that? Because our implementation also generates the mechanized proof in the Abella proof assistant. So we have a bunch of mechanized proofs. Our primary goal is instead linguistic. So we want to give the linguistic tools to express well-known proofs, but in a way that is akin to pseudocode that apply not to one language, but to classes of languages. So our question, back to our question, can we create DSL to express proof schemas? And we can see this in three simple, fast steps. So the first step is our DSL, so a proof language for language proofs. And the first part is the language to express proofs. The first part is quite standard, so we have intros to introduce the proviso of the theorem, search to tell that we have everything in our knowledge to conclude the proof, case analysis, induction, apply theorem, sequentializing proofs, and so on. But then we also add a couple of instructions for each statement that is going to sequentialize a proof for each element z of a list T. And also we have an if then else. Okay. But the biggest part is actually here with the language for expressing theorem and actually for writing and also for writing inside the proofs, like inside the if then else and so on. So we are going to see only a few elements of Langen proof, and in the slides we focus on the 3 elements. The theorems can be created with a for each also. Then we have a way to produce names, and we have this C name that it's just the name of a syntactic category from the grammar. So we can see we can use these 3 elements, for example, here with the code below. So for each tie in type, so for each element of the grammar type, okay, we create a theorem called the canonical form, and we append tie, which is going to grab the top level operator of the type. So basically, with just this line, we can create the theorem canonical form list, canonical form pair, and so on, canonical form arrow for the function type, and so on. Okay, so basically this is the way Langen proof gives linguistic tools. Now we can continue to generate a formula. For example, for the theorem, we have a generalized implication that creates many implications in a row for as many elements or elements z of a list T. Then here we check whether a term, an expression, is an elimination form. So this is an useful for an if then else, so that we can do cases, proof cases, distinguishing the role of operators. And of course, so is elimination form when it's applied to the application holds, when it's applied to head holds, and the for cons doesn't hold. And we are going to see, we also have is error handler to test whether it's an error handler and so on. And the derived operators like let declaration. Now, we are not going to see all of them. We see get archetype. Basically, here we have an example. So the first element, so the first argument of app, so the zeroth element of app. What is the type? Well, it's a T1 arrow T2 because we are going to grab it from the typing rule and the premise for E1. Okay, and similarly, we can have the type of the first element of head. It's going to be list T because we look at the the DSL is going to interrogate a language definition given in input. Okay, so the operator contextual args is going to give the arguments. So the index of the position of the arguments of an operator that are subject to an evaluation context. So evaluation order does the same, but provides this list with the indices in the evaluation order. Okay. So, for example, it's 0, 1 when the application is evaluated from left to right. It's 1, 0 when it's evaluated from right to left. Okay. Now, we have implemented Langen proof, and we are going to see an example of a proof schema. So, Langen proof takes in input a language definition and a proof schema written in this way, and interrogates the language definitions in order to create a proof that is then compiled as a proof code of the Abella proof assistant. Now, I've said the language definition, and I said that it's operational semantics. So here, just to give an example, it's just a textual representation of operational semantics, and there's nothing novel about a notation like this when it comes to defining languages. Now, step number 2, let's see an example. So, and with this example with the progress. So we have divided the progress theorem into 2 parts. The main part, and we will see. Now, first, we have to tell the target, because of course we didn't give the progress theorem for any language that we can think of. So what is the languages that we target? So the paper goes more in detail about this. So here I have to be a little bit quick about it. Let's say that it's purely functional languages. So so the reduction is from it's a rewriting of expression to expression, no state, and where the operations operators can be divided in elimination forms and introduction forms. Sometimes it's a property called harmony, and yeah, and so the paper goes more in detail. So these are simple functional languages, but the class it's quite grabs several functional languages. So okay, so when it comes to this a proof schema for the progress theorem. So here the predicate progress is the one, okay, value, error, or takes a step. So line 3 we do an induction. Then line 4, okay, we repeat the proof code of lines 5 and 6 for each expression. Okay, so the expression, so from the grammar of expressions. Okay, for each of them we are going to apply the inductive hypothesis. So to derive that the arguments themselves progress. For the contextual argument. So in line 5 we have a repetition for all the indexes in the contextual arguments of the operator. Okay. Now here tip I comes from line 3. So because when you open a case like an induction, there may be other premises. For example, the typing formulae of the arguments of an operator. Okay, here we have the assumption that, for example, type 0 is the typing rule of the first argument, type 1 is the typing rule of the second argument. So there is an assumption there. And line 6 calls what is called an operator-specific progress theorem. For example, for application, it's called the progress app. So that's why there we create a name appending the operator, the expression. And these operator-specific progress theorems basically just say that if the arguments progress, well, then the whole application progress. Okay, well, of course we have to prove, and then the next step is we will see. So when it comes to the progress theorem, if you want to apply apply this schema to the language that we have, here is basically the proof code that we get, where after induction we have all these apply the inductive hypothesis, and then backchain the theorem that is going to conclude. So backchain is going to conclude the proof if the theorem is applied. Can be applied. So now these progress-specific, operator-specific progress theorem. So there is one for each expression. So the first line will create progress app, progress head, and so on. Okay. Then, as we have seen, a part of the theorem of these progress theorems is that in the middle you have all these premises that says that the arguments progress. Okay, and this is how we created with the generalized implication for each index that is in the evaluation context. We are going to basically put a formula progresses, and where we do with getArg, we just gets the argument of the expression that comes from the grammar from line 1. Okay, basically puts this this premise. Okay, and also we give a name called progress E0, progress E1, and so on. Okay, at line 4, for each of these premises, we do a case analysis, and we do this case analysis in the order of evaluation order. And now I will explain why. But here, just to say, here we have an example of what this creates. So for the application creates the name of the formula progress E0, and the formula is progresses E1. Then progress E1 is progresses E2. Okay. And the proof is that it has this case analysis in this order, case progress E0, case progress E1. Now, we follow the evaluation order, and we can see a visual about that. So when we do a case analysis on the progress of the first evaluated argument, we have 3 cases. That it's a value, an error, and takes a step. From there, so operating from there, if we do a case analysis on the progress of that, of the second argument that needs to be evaluated, okay, we get other 3 cases, and so on. So basically, at the end, we end up at the leftmost case. That is basically the case where all the arguments that needs to be evaluated are values in that case. So then we have a chance to apply one of the reduction rules, like the beta reduction rule applies only when both function and argument are values in call by value. So basically, we are in that, and so we can programmatically say, okay, I'm in that case, and what we do is in lines 6, 7, 8, and 9, it's an elimination form. Then line 7 is going to apply the canonical form, and we're going to retrieve the type of the first. So the thing is that we also have the assumption that the principal argument is always going to be the first, basically. Okay. So for application, the function is the first argument. So for head, of course. So basically, we get arg type, we get the type of that, and we append it to canonical form to apply the correct theorem. Okay. Once then we have to dismiss all the cases of the of all the canonical forms. Okay, and the line 9 does that. So for each value that is in values of and that type, and we didn't see values of, but here we have an example in tutorial. When you have values of list, you have there the list with empty list and cons. Okay. And so for each of them, we apply search because it's appealing to the existence of a reduction rule. Basically, you say that we have everything, so the proof has everything to conclude. Okay, so we do line 9 does that for each value of the type that the elimination form is type of, basically. Okay. Now, step number 3 is our evaluation, because I've just given an example. Of course. So we have written the type safety proofs, the type safety proof schema for this class of languages. Okay, so the canonical form lemmas, progress theorem, and type preservation. But type preservation relies, and only the type preservation relies on the substitution lemma, and we didn't cover that. And the reason for that is because the substitution lemma is strongly dependent on the representation of binders, and we didn't want to commit. So as future work, we would like to address that in a way that it's representation agnostic. So yeah, we applied our type safety proofs to several functional languages, and functional languages that the simply type lambda calculus with integers, booleans, pairs, lists, recursive types, universal types, and so on, lists, and so on. Yeah, we could generate the valid mechanized proofs for all these languages. Okay, when it comes to the type preservation, we had to provide manually the substitution lemma code for that. But again, the substitution lemma is just a small, really small part of that. So in the paper, to conclude, in the paper, you can find the full DSL, the full progress theorem, and also the other proofs, and also the compilation from proof schemas to actual proofs. And for future work, we would like to develop more proofs addressing the substitution lemma, for example, and subtyping. We would like to develop debugging tools and integrate LangImprove with language workbenches. Okay, thank you.
Okay, we have 1 minute for questions. Any questions?
Sorry about that.
So I was going to ask about subtyping, as you have that on your slide already. So I asked about state. So how would that work?
Yeah, good question. Because when it comes to the proofs of these functional languages that we cover go. So at least in this class go always in the same way. But when it comes to state, any language has a different state and different mechanisms. So I am not sure, to be honest. I am not sure. I hope we can generalize that, maybe thinking of the states in a monadic way, and so basically whichever is the state, maybe a proof schema can be done. It's future work. Thanks for the question. Sorry, I don't have a more precise.
Yeah. So are we done? Oh, okay.
Okay, let's thank the speaker again.